Welcome, my best chemistry students. It is good to see you back. Believe it or not, we are quickly winding down. This is video 15 of this series, and it's the last in the notes, and it will be followed up by 2 videos doing some AP questions so you can get a sense for what those are like. Now we have 2 concepts left in this portion of the atom, and the first deals with excited states. Remember, in an excited state, an electron has gone from a low energy state to a high energy state. Now remember too, when we do a ground state configuration in the, when we do the electron configuration, we're following the Aufbau principle. That's the build-up. So if a configuration follows the periodic table, like I taught you and like you're going to be practicing with, if it follows the periodic table, then that's going to be a ground state. Because that's how we've laid that out. That's how it follows in always entering into the lowest energy state first. Now, there were a couple of typos that I caught in the notes. So if you want to check that, instead of 3D5, that should be 4D5, and that should be 4D8. So you want to go ahead and fix those typos before I get going. Now, what we want to do first is do our identification. So this is identify by looking. That might be a multiple choice question. And then we're going to justify. That might be one of your short answers on a test. And remember, that's where we're really learning how to articulate our arguments. So that's going to be a critical one. Now, what you want to do, and maybe you'll need your periodic table for a little while to do this, but you want to go through here and first off, make sure that they are in the order of the periodic table in terms of energy levels and sublevels. So it goes 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s. And that's correct. That is the order. Now, next what you want to do is take a look at the numbers of electrons in each of these. And if they're maxed out and nothing has hopped higher, and be careful, watch those little irregular ones, then it's likely to be a ground state, as is the case here. So this would be ground state, and to justify, you would want to make a statement that all electrons were assigned based on the Aufbau principle. And therefore they're at the lowest energy. Okay, so they're all, put a little, therefore low energy. Now, in this case, you've got to be a little careful. Again, and you can kind of match to the ones above it here, these are all in the right order, but there has been a hop here from the 5s to the 4d. So when you see an S to a D hop, one of the first things you need to check is, could this be one of your irregular configurations? Don't just assume that an S to a D hop is an excited state. And this one happens to be the element molybdenum, and it is an irregular, so it's ground state. And you would justify similarly above, and also, so same as above, but also mention that it's an irregular configuration. Now, as we go through this one, we're seeing everything in the right order, except, let's take a look here. Now look at the electrons. When you look at the electrons here, almost kind of obscured it for you. When you look at the electrons in there, do you notice that one electron went from the D to the P? That's higher. That's a higher energy state. So that would be your excited state. And your justification is the electron configuration should have been 3D10, 4P5, and one electron went to a higher excited state, 3D9, 4P6. Now you need to use a few more words than that when we're on a test. All right, so now, and then this last one, this follows through. As we go through, we see the order is correct. Again, walk through your periodic table for a little while if you need help. And then we check the numbers of electrons, and lo and behold, they are correct as well, and so that's a ground state. So that's how you look to see whether something's an excited or a ground. Now, let's look at how we form ions. When we're doing ion configurations, we're going to be looking right now at the representative or main group elements, not transitions. Some of the transitions are really obvious from their periodic or from their electron configuration, and some of them are not quite as obvious from their electron configurations. Now, let's take a look at lead first. And to do this, I'm going to go ahead and use our noble gas because it's only the outer electrons that are going to be involved in bonding. So this is 6s2. It would hop down to 4f14, come back up to 5d10, and then to 6p2 would be lead. Now, when we make ions, what we're going to be doing when we remove, we'll be removing from the outer S and P sublevels because they're furthest away. So the furthest away are the most likely to be removed, or really to be attracted to another nucleus is truly what's happening. Remember, it all comes down to attractive and repulsive forces. And we have a special name for those electrons. The outer S and P electrons are called valence electrons. And so if we look here at our lead, we see we have 6s2 and we have 6p2. Are our outer electrons. Now, lead happens to form two ions. The first one I'm telling you is +2, and it's going to lose the p electrons first. So we would end up with xenon 6s2 4f14 5d10. We would lose those 6p2 electrons. Okay? We always lose our valence. The others are called core electrons, and we're not going to be losing core electrons. Now, to get to the 4+ stage, so we have lead 4+, we would lose both the p and the s electrons. So it would be xenon, lost the 6s2, so we'd have 4f14, 5d10, and we've lost the 6p2 as well. So we would lose the 6s2 and the 6p2. That's how lead has those two charges associated. And if you look right above lead on the periodic table at tin, tin does the same thing. Tin has two charges, +2 and +4. And you should be able to predict those and not really have to memorize them. Now, barium. Barium, you've heard of that old joke, haven't you? What do you do to dead scientists? You bury them. Okay, sorry, that was pretty bad. All right. Now, barium is a group 2. Those are your alkaline earth metals. And I'm telling you it's 2+, but you know that by now. You know that barium group 2 is always +2. It loses its outer valence electrons. So let's go ahead. That's what we would be losing here. And so for barium, it actually achieves that stable state of xenon. And we call that isoelectronic. We're going to see that word again later, but it's isoelectronic. Same electron configuration as xenon has. And now I want you to predict the antimony. Antimony is krypton, And then from krypton, we'd go to 5s2, 4d10, 5p3. Now remember, we're dealing with the valence electrons, which are our outer s and p. So if we lost the 5p3, we'd have antimony 3+. And that is one of the main charges of antimony. Now, if we lost both the 5s2 and the 5p3, we'd have antimony +5. So those would be our ions for antimony. So you should be able to predict ions for all of the main group elements. There's some other ones like zinc and cadmium and silver that are also pretty straightforward given the periodic table. There's some that we don't use as much, scandium and titanium and vanadium, those three groups. That's 21, 22, and 23. Those families are fairly predictable as well. All right, the next videos you'll watch will be AP questions. Until then, this is signing off.